Hi, I'm Charles Tapiero. I am the head of the Department of Finance and Risk Engineering at the NYU School of Engineering. We are a department that deals essentially with the mathematics and the engineering of the future of finance. Part of it, and an important part of it, of course, is bridging the gap between technology and finance and bridging the gap between theory and practice. So what I'm going to talk to you about today is just sort of an introduction to what I would call extreme risks and finance. Uh, well, because of the lack of time, I will not be able to cover all the topics and all the applications we ought to consider, but of course I will try and say a few words. Okay, extreme risk and finance. Allow me to close the light so you can see better. Okay, uh, let me say this, something about what extreme risks are all about. There is a problem, is that the problem is that the way we have approached the concept of extreme risks. And I would like to present an alternative way to look at it. For example, conventionally, what we do, we define extreme risk by their rarity. In other words, by associating to them what I would call very small, very rare probability. On the other hand, we associate to it an extremely high consequence. And so basically, this consequence and this type of element is really reduced to what we call fat tail distribution, which basically in finance means we don't know what's happening. So let's put it that way. Fat tail distributions are simply distribution to replicate our lack of knowledge. The measurements also of extreme risks are really ill-defined and for a number of reasons. First of all, we have to understand that there is no statistical evidence that would allow us, in fact, to construct distributions. That's number one. Number two is that their existence is neglected in prior statistical models because, as the Greek used to say, the unlikely is likely. So whatever we think is going to happen is not happening. And so extreme risk belong to the domain of the unknown unknown. Third point, they recur temporarily over extended periods of time, and therefore the key element about modeling or thinking about extreme risks in finance and as well in other area is really time. How long do we have to wait for time to manifest itself in terms of an extreme risk? And second, of course, is the consequences. So, in fact, extreme risk need not be rare. I do not know why we associate to extreme risk a rarity, because they happen very often. I mean, almost predictably, if you look at banks and we talk extreme risks of banks, they happen every few years. We have whole statistical data that simply shows that extreme risks in finance, the breakdown, crises are happening everywhere and quite often. Now, basically, what are extreme risks? Extreme risks arise for many reasons that have to be distinguished, and there is not one approach which really is appropriate for one type of model. For example, they can be endogenous, in other words, resulting from what men made, One, they could be exogenous, like, imagine a nightmare falling upon Earth and killing whoever can stand. And then, of course, there are also what I like to think hybrid. By hybrid, it simply means that they combine elements that depend on endogenous factors, but at the same time are perceived as being exogenous. I would put under this category, for example, global warming, and of course, what people use their car, use the kind of how we affect our environment by living on this earth. Basically, I think that extreme risk could be surprising. If they're not surprising, then simply, we should have known about that. They could have been predictable. So when they are surprising, I think that they can occur because of statistics, probabilities, or if you want to talk about them, those terms, they don't exist, but especially because of complexity. In other words, they really come from a lack of understanding, from a lack of knowledge. And that's a very essential point. Try to think, what is an extreme risk? It is something that falls upon you that you did not predict. Because if you were able to predict it, then of course you would have been able to protect yourself in some way. So there are many factors that you can read in those elements here that I've been writing here, including there could be risk externalities, especially when they really occur and somebody is man-made, and then, of course, the environment changes. Okay. Now, I believe that fat tails are not appropriate, and I like to say exactly why. In a few words, because I really would like to go a little further. Okay. I would just talk some element. Are they outliers? If they are outliers, they don't belong to any population we seem to study. Are they discrete events? If they are discrete events, then what really matters is the time between their happening. I believe that they underlie essentially bifurcating dynamic processes that are complex and chaotic, and they converge to extreme events. For example, when you look at financial markets, then financial markets comes from behaviors that are inducing a chaos in some way and leading financial market to be out of equilibrium and then simply breaking down. And I think that when we talk about them as statistical financial model, it is wishful thinking in some ways because they are extremely complicated. Now let us define what is extreme risk mathematically, and this is really the underlying approach I like to just elevate. And of course, I like to add that this is some research I'm doing with Pierre Valois from the University of Rennes. And basically what it is that extreme risk distribution are implied. Are implied in what? In the hazard rate, which defines the amount of time till an event can occur. And usually the hazard rate has to be a very, very small probability, because if it is very common, it will have a high probability. So the question, how can we construct model from hazard rate, in other words, from time, that have a very, very small hazard rate? In other words, we would feel safe, but its consequence might not be so safe. So now they may be interacting among numerous risks factors, and I think the 1 and the 2 could be modeled. I will show how. But I will show that in a way which I believe is new in the context of how to approach this problem in terms of fractional, what I would like to call statistical fractional calculus, which is something we are developing. And of course, there may be dependent, which is the common way to say that things depend on one another. Consequences are extremely large, ill-defined, and of course, contagious as well. There are many causes, so I would leave you, if you get this, you will get probably these files. I'll leave them very fast. It's many reasons. There are many, many reasons. These water disasters. If you go to some financial, or if you go to some insurance firms' websites, you probably will discover a lot of data that tells you how things happen in terms of their intensity. Okay, let's say something about finance. But what finance is this? We have to understand financial models are basically exchange models based on a market environment where risk distributions are mostly normal, defined by independent financial agents based on an implied known future prices. This is simply mathematically formulated because it is based on a number of assumptions which I assume that all financial engineers and financial mathematicians and most people know. And they are based on a rational expectation model resulting in underlying processes with the price defined by a martingale, unique and specific to the market price. Pricing models are then simply a theoretical anchor. So this is sort of important because the financial models are basically equilibrium models, which means they never exist. They only exist as relative to what is happening in market. In other words, it is something that we believe might theoretically exist. Now, if I look at the hazard rate, and I will relate this hazard rate to the probability distribution for extreme events and finance, is that it is a function of time. Second, fractional hazard is what? Is a conditional probability distribution that is fractional. And by creating such a distribution, I would like to say the following, and that is the key point, is that such a distribution has an implied probability distribution. And that implied probability distribution is a generalization of the hazard rate. And it has the property, according to the choice of the fractional rate, to the fractional rate that we choose, it had the following property that it can increase the time. So even if I were to take a certain distribution that is, has a very small probability associated for having, I can make it even smaller. I can manipulate it simply by the manner in which I'm going to fractionalize that particular element. And second, I change automatically its distribution. And I change in distribution in two ways. A, which is much more symptomatic and an example of the kind of things we have in risk finance, is what? Is that the amount of time for an event to occur is bigger on the one hand, and then on the other, there is another element, is that it is more uncertain. So I would say increasing the amount of time and at the same time, parametrically, and at the same time, increasing the uncertainty associated to that time really create an environment or create assumptions that are far more compatible with what we call the world of extreme risks. Okay? So the question is now, of course, this differs very appreciably for what we call fractional Brownian motion, because fractional Brownian motion is what? Is really two things. First of all, it is a volatility that has been fractionalized. In other words, a linear function of time, which is fractionalized, and is associated to a distribution that in fact does not exist, because the fractional Brownian motion does not exist. Okay, so having said that, let me go further. Just look for some mathematical development. Let us take, for example, the cumulative fractional distribution. Then using the Riemann-Liouville operators, then that distribution is defined, cumulative distribution is defined by the, well, as you can see, this is the probability distribution, which is not fractional. And of course, when it is integrated, it gives you this particular results. And if I want to find out what is the fractional probability distribution, then it is equal to the derivative, the fractional derivative of the cumulative distribution. So it is easy to show. I mean, we have shown, Pierre Valois and myself, that in this case, those distributions go to infinity and they do not exist. For example, but if I were to calculate those distributions in terms of as a function of a random, normally a uniform distribution in 0, 1, then I can prove that basically that distribution is equal to an expectation of this function, where u is a random variable. And therefore, the randomness implied in a fractional distribution is really embedded, is a function of this particular uniform distribution. And of course, I can go and prove it, and these are the proofs, and so on. So if I were to use the exponential probability distribution, then it is easy to show that that's a cumulative distribution, that is the results, and of course, and when you could see that I will show that it is really in fact infinite, and if the cumulative distribution is infinite, then of course, then it does not exist. And therefore, probability of distributions that are fractional, defined from the fractional time associated to distribution, simply do not exist. However, their moments can be calculated in some way. All right, if you have a compact support, it's very different, because if you have a compact support, then I would say that, let's say K here, not infinity, but K, then of course what we have here, we have an exact solution, and this is a probability distribution. So the idea of providing a compact support always yield to distribution. But distribution do not have always a compact support, even though we believe it can be used as approximation. So if I were to look at the expected value, let's say, with respect to a fractional distribution, then I would say its cumulative distribution, which is by definition this, is equal to infinity. And if it is infinity, it is not a distribution. And if it is, of course, if it exists, if it is a compact support, it exists, and it is simply this particular equation, which is not particularly new, which can be found almost everywhere. Now, when you look at randomness and you take this particular distribution, then you can prove that that distribution is this one. So randomness is now defined differently. than a normal distribution, but also it doesn't exist, because if you were going to study that, you are going to find that this cumulative distribution scales to infinity. And therefore, the whole question, when we talk about statistics, and when we talk applying fractional calculus to the elements of statistics to do apply in finance, because all of finance is uncertainty, risk, statistical based. And therefore, what we do, we need an approach that leads us to distribution we can use, and we can communicate with because they do exist. So here comes what we want to do. So I'm going to take a simple example, and then I will just mention a few applications, and then I will end. How much time? Okay, so basically here is the fractional rate, and if you you look at it in this way, and therefore if you want to look at the fractional hazard rate, it is equal to the fractional derivative of 1 minus ft. So interestingly is this, the probability distribution is implied, and the keyword is implied by the fractional hazard rate. That's number one. And number two, a probability distribution exists and is well defined. So let us say, first of all, let us take a regular probability cumulative distribution. The cumulative distribution is 1 minus exponential, the integral of its hazard rate, and therefore, and the financial and the probability distribution, which is implied by a hazard rate ht, is really equal to h of t times the exponential of the integral of h of t. Having said that, I would take the same thing in terms of a fractional hazard rate. And what is this cumulative distribution? The cumulative distribution is equal to 1 minus the exponential of the fractional hazard rate. While FHT is equal exactly what I wrote here. It is really defined in terms of the hazard. So if I were to take an exponential probability distribution, or even a generalization, it would be extremely simple to show that the fractional hazard rate has this particular form, which in fact is what? The fractional rate of a Weibull distribution. In fact, I would say that all hazard rate, which is polynomial in the sense that it has a tau power alpha or beta or gamma, results in a Weibull distribution. So the Weibull distribution is very robust for this type of hazard rate. But it's not all. If I were to take, for example, even a gamma distribution, then I would take the gamma distribution and I would find that it is also leads to another distribution, which is also sum of Weibull distribution. If I were to look at the expected value and the variance of time in that distribution, what do I find? I find that for an appropriate h, which is 0 and 1, then I would find that the amount of time increases. What does it mean that the amount of time increases as a function of h? It increases because h, when you calculate the fractional distribution, it expands time. So if it expands time, of course, it renders the model of the event occurring bigger than what you have assumed with the simple exponential or even the Weibull distribution. But what happened to the variance of t? It increases. If it increases, what does it mean? It means that you have greater uncertainty. Now, when we talk about extreme risk, what do we mean? We talk about something we know nothing about. So increasing its time, implied probability. Increasing its what? It's a variance. What does it do? It really creates a problem that is even less known. So really, by pushing h, you can eventually go to a model where you are dealing with distributions that are really very little known. And it's parametric. Now, okay, these are sort of obvious. Now, the question is this. It is different from the fractional normal distribution because fractional Brownian motion is not a probability distribution. And second, fractional Brownian motion simply says, if I were to look at the work of Meltzer and Klafter, from Tel Aviv University, then I would point out that, if you take the Fokker-Planck partial differential equation and you fractionalize it, then you can obtain all kinds of distributions. So it is not unique, and it is very complex. So the question comes up is this, okay, what is it good for? Well, this requires a lot more study. Okay? Now, this has very important implications to extreme risk for finance, for insurance, for high-frequency trading, for risk management, and so on. I will just give you very quickly. In insurance, the Gompers-Meckham probability distribution is often used, simply for life predictions. Now, it is important because the Meckham distribution assumes a certain independence at the aggregate level, while the Gompers distribution assumes a certain independence at the individual level. But when you look at that, and this is the distribution you have, but when you look at that, that is the hazard rate. Now, it is very convenient because what you can do, you can, with very little data, you can try and estimate by regression the parameter gamma, alpha, and beta. Why? Because one is linear in time, once you take, of course, the lambda for that, and these are estimable. So the whole question of being able to relate little data to a complex model might become a lot easier if you can have a decent expression for the hazard rate. So when you do that, you obtain now the cumulative distribution is equal to this. You have that. So if you have this, you do have an expression for the probability distribution of life, which is far more broader than what we have used, and therefore we get a parameter which we can estimate at least through this kind of equations. So here we go. So we have now one FH of t. That would be the probability of life. So, and when, of course, when you look at that, this is a Mittag-Leffler function. I do not want to go into that. I am going to go even more. If I want to go to an Erlang distribution, this is h of t. Here it is. You can study it. You can do that, whatever it is. Now, there is a result. This is a very partial result, that which is expanded in one of my papers with Pierre Valois, and of course we are going to we can make it available. It is this. It is that when you look at VAR, there is a real problem with the application of VAR. So the question is, can we fractionalize VAR? I believe yes, but you have to think of VAR in a different context. You have to think of a time VAR. In other words, if you put some money aside to protect the firm from its liquidity, then what matters is not the probability. What matters is the amount of time that one can reach such a breakdown. And that is the key question. So we did solve the issue of time. Why? Well, we use what we call surrogate models. When you use surrogate models, you calculate the first time to a given state. When you fractionalize that time, you move to another family of distribution which are much more tolerant of a great variety of situations that are not accounted for by the distribution we usually use. And therefore, if we want to regulate in a way that is far more stable, far more consistent, we have to turn to fractional calculus. I will not say how, what, and where I can do that. I'd like to add a little more before I do finish. I can just tell you the same thing with power laws. I take a power law, and that is the fractional hazard rate. And of course, this expression, because it is bounded, I can calculate it. And of course, I do have the distribution that extends, generalizes the family of Pareto distribution. Now, I have attacked only one problem, which is one risk. But in fact, we generalize that to multiple risks at the same time. By generalizing that to multiple risks at the same time, we understand the complexity of the world. That is not single risk, but multiple risks that may interact or not. But we are always hit by the worst one, which happen with different probabilities. But you may have the best of cases generating a disaster that you would never have estimated, because life is unexpected. So having done that, when I look at this in those terms, it leads to another family of model, and I think that would be good for the next talk. Thank you very much.